Let's do this. All right. Welcome, everyone. July Dev Night. Heck yes. Who goes to school here? Really? I figured like half of the crew would be like students.
We tried.
Okay.
And it's even here, so like.
I mean, I'm starting in the fall.
Okay, how many other aspiring
Gonna come
matriculating
out and
here
go
in
to
the fall? All right. Okay, cool. Well, we're pleased with the turnout. This is awesome, especially for summer months. So awesome. New venue means new audio stuff, so bear with us if there's any fumbling going on. That goes for the remote audience as well. So before we get started this evening with our game development talk, number of announcements to talk about, and there will be some more next month. So pretty exciting things. Now feels like things are really ramping back up to usual status, so that's cool. And right as that's about to happen, we've got some big things going on. So we'll start with small and grow up a little bit. So first thing is the website. If this is your first time seeing this, the URL is sgf.dev. We've got a directory on here where we would really like everyone to sign up. It's free. The big thing here is just getting all of our members in this directory. So perhaps if you're looking for somebody to collaborate with, hire, just hang out with, whatever, you got this directory to come check out. You can sort by skills and all that good stuff. But then it's also really great for employers. So we're starting to get more sponsors in. And when you sign up for a profile, you've got the option on there to check whether or not you are looking for freelance work, just project work, or full-time work. And the companies that we partner with, if you elect to be seen as such, they will be able to reach out to you. So this is kind of a very qualified way for people to find one another. So please sign up. Another note on the website is if you are signing up, if anybody does that tonight, you'll probably be the first one to sign up on the newly updated site. And, wouldn't be surprised if you hit a snag or two in that process. So if you happen to do that tonight, find me, show me the error, and that will help out a ton. Also on that note, this site was built on a CMS. If you know anything about me, you know that I'm a raging fan of the Embraco CMS. This is built on that. It's a .NET content management system. When we first released the site, now back like 2.5 years ago, it was built on a version that required you to run an older version of .NET, which also required you to have a Windows machine. It's no longer the case. .NET Core has come out, .NET 5, .NET 6, all that good stuff. So it's all been updated. It can run on Windows, Mac, Linux. If you're interested in getting involved with helping out with the site, there's a huge list of things we still want to do on here. Bugs, all that good stuff. It's all out on our GitHub repository, link at the bottom of this site. If you are interested, I just put up the documentation for how to get this up and running locally. Really looking for some people to go through that process and provide any feedback on what the setup was like. So if you're interested, I urge you to do that. That's kind of it on the site. By the way, if this is the first time you're hearing about this is monumental. Like, we've been working on this for a long freaking time. Updating this thing was a bear. It's finally done, and it's exciting. So there's that. We've got a guest here that I'm going to introduce here in just a moment. But before doing that, we'll talk about the big news going on. So if this is first time attending or maybe newer to the group and don't kind of know some of the history, I'll give a super abridged version of it. I started the group Springfield Web Devs something like 7, 8 years ago now, I think. It was kind of a passion thing of mine. I funded it out of my own pocket. It ran for several years, and there's been very, very, very few months where we haven't met. If anything, it was due to weather. And so it's been going steady. It's been going strong. I'm getting busier with stuff, and and like ultimately wanted to make sure, that this group could live a life, past me, trying my best to organize it. And so that's why Springfield Devs became a formal nonprofit entity. That's been going pretty cool. We had our first conference, and one of our speakers there actually from the conference. Yeah, just walked in. Hell timing. Talking about method. Yeah. So it was really cool, and then COVID came along and just like derailed every freaking plan that we had. So there was a couple of years there where, like I said at the beginning, we're starting to get back to normal now. But as part of that process, we had a formal board of directors and formal officers on that board. And so what we had was these three roles plus a treasurer, which is not pictured here because we have a treasurer. And what's going on now is the officers are finally cycling our 3-year terms. What's that? What?
They're all Mike Bates.
Oh, damn it. I was prepping this right before it came, and I was copying, and shit. Okay, so Vice President Tom Rankin and Secretary Shauna Barron. Super sorry about that. Wow, what an ego on this guy. We will be cycling out of our roles, and just before this session started, we voted on members who applied for these roles, and so this is, oh man, so I'll zoom in, come on, whatever. I tried making a torch, passing the torch here, but it's all zoomed. So I am happy to announce these three roles. Come on. There we go. Hey, now we're zooming out. Oh, yeah, so our new secretary, Mike Bates. Tiffany Ford is our new secretary. She's been on the board for... Yes, please. There we go. Yes. Thank you. Yes. She's been on the board for quite a while, instrumental in so many things, not the least of which is managing all of the dev nights and everything behind the scenes there. So she's going to be a very natural fit in the secretary position. So thank you, Tiffany. And zoom out here. We got our vice president, Melissa Hamilton. Come on, there you go. So Melissa has been behind the scenes of a lot of things as well. So she works over at the E Factory and has been instrumental in us being able to live over there, thrive over there, puts up with all of our horse shit. And she's just fantastic. She's got great vision for goals for this group and how it will evolve, and she will be a fantastic VP. And last but not least, if we want to throw a round of applause together for our president, our new president, Levi Zitting. If you've been hanging around the group much at all, you've very likely seen Levi. Maybe half of his family's in here, I don't even know. But Levi's freaking awesome. He showed up out of the blue to one of the meetings, kind of like, 4 years ago, yep. Shows up and, he's just like, I'm new. And, start talking to him and find out, damn kid's a genius. So, no, seriously, Levi's amazing. Not only an incredibly skilled developer, but has been doing a lot in the community. Not only helping out with our group, the conference, everything going on, but has started your own group, been doing lots. And I suspect that passion is going to be brought right into Springfield Devs as well. So, the treasurer role was one that was left out in there. So we do currently have a treasurer, Landon Lewis. Some of you may know him. His work life has gotten exceedingly busy. And so he's really wanting to try and find somebody to transition this role to. So I bring this up today just to say if anybody has any experience even like opening and reconciling like a line item in QuickBooks and are interested in serving in this role, hit me up. We're going to officially put this out online here probably within the next week or two, I would imagine. So at the very least, be on the lookout for that. If you come talk with me, I'll be sure to follow up with you and let you know right away when that comes out to apply for. But yes, we're going to be looking to fill that as well. So those are the big announcements. I mentioned we have a guest in here. I'm going to try and partially switch modes to start to cue this up. Yep, that one cool. Okay, so I don't know how many people know about the eFactory and Codify's partnership that's going on. If anybody does, maybe raise your hand so I can kind of get a feel. Couple. Yeah. Of course, Melissa knows. In fact, hopefully I don't butcher explaining much of this, and if I do, you can come up here and correct me. So I'm not going to speak too much on it, but just know that you probably heard of boot camps. Obviously, we know about colleges, tech schools, universities, what have you. So eFactory has partnered with Codify, and they are starting several things. But the first of which is I don't know. Do we refer to it as a boot camp? What is it called, Melissa? Boot camp. All right, cool. But I think the hugely important thing here is free. Right? Yes. Okay. I don't want to speak wrong there. It's free. It's got a heck of a curriculum. It's in the evenings. You can attend in person or online. Pretty huge deal, especially something being for free. I mean, that's amazing. But one of the other things that goes on at Codify is a youth coding league. And in a second here, I'm going to turn it over to Stacy here. But just know that. Yeah. Oh shit. Okay, well, she doesn't get to hear her intro then. I'll unmute. So I'm going to introduce her here in just a second, but just know one of the reasons that she's in here talking to you all today is looking for volunteers, looking for people to get involved with this group on a number of different levels. And I'll have Stacy talk about that right now. So.
Hello, can you guys hear me? Okay, I cannot hear you, so I'm going at a little... Okay, I'm just gonna go. Hi, thank you guys for having me and for letting... No? Okay. Thank you guys so much for having me, for letting me barge in on your evening together. My name is Stacy. Perfect. I was at the eFactory a couple of weeks ago as we announced some big programs that we're rolling out. I work at Codify in Cape Girardeau, just across the state from you guys. And we're rolling out some projects in partnership with the eFactory and the amazing team there. One of the programs that we're getting the opportunity to roll out to your area is funded by a grant through the Missouri Technology Corporation that is funding youth coding league teams at schools in the Springfield and Southwest Missouri area. So that's why I'm visiting with you guys tonight, because 8 of those teams are at Boys and Girls Club locations. I'm going to pop in the general channel for this Discord, all the details of what I'm talking about. So you'll have it all there for your reference. But the Youth Coding League is something that the devs in our office always wished was around for them when they were in 5th through 8th grades, but we've basically turned learning how to code into a sport. We use Google's CS First curriculum. We've built in our own competitive element on top of that curriculum, and every single week we upload scores to youthcodingleague.com so kids can see how they're doing both individually and as part of a team. So it really has a feel for like an esports leaderboard every week. We also have a competitive postseason where the kids build out group projects, and then they're competitive in a couple of different bracket style competition series. Our heart on this is to make sure that the kids who need this the most, who aren't going to get it at home, have the opportunity to access this skill set. So we really specialize in rural, high poverty, under-resourced school districts. So getting the opportunity to work with the Boys and Girls Club in Springfield, which is already such an incredible organization, is such an honor and a privilege, and we're so excited to be there this fall. So they've asked for volunteers to help support their staff as they roll out the Youth Coding League at their 8 units. I don't have details on when they're meeting just yet, but they tend to meet after school during the week. The kids meet for about an hour and a half to 2 hours at a time, and they've asked for volunteers to just come in and help the kids troubleshoot their code. They're building projects in Scratch, so hopefully you guys can handle that programming language. I feel like you can. Have some help troubleshooting in Scratch when things just aren't quite working the way that they should. But really, I've been in the classroom a lot since we launched this program in the fall of 2018. The kids crave being able to show off their work to an admiring adult. So honestly, one of the most important roles of YCL volunteers is kind of oohing and eyeing over their project and what the kids came up with. So that's another big component too, is just really injecting that like praise for the kids as they work really hard on their projects. So we will have kind of 9 to 11 week long, once a week, after school for an hour and a half to 2 hours at a time, volunteer opportunities available with the Boys and Girls Club. If that's too much of an ask for you, we also do technical merit judging in the postseason, and we work with local devs. We've been working with local devs in Cape Girardeau, and we'd love to expand that to your area as well, where you guys get to go in and anonymously view the kids' group projects and then score them according to a rubric. And the projects with the highest scores get to advance from round to round. This tends to be like a one-time 2 to 3 hour time commitment, and we run those over Zoom. We have a special scoring dashboard and everything, and we try to make that as easy and as streamlined as possible for you guys. So really, 2 different volunteer opportunities, one landing more in November. It's kind of a one-off during the workday on Zoom, a couple hours, and the other one a little more regular and consistent during the regular season and while the kids are working on their group project once a week for an hour or two after school at a local Boys and Girls Club location. So would really value any time that you're able to give to these kids as they learn how to code and access computer science, sometimes for the very first time. And again, I'll pop all my details over in the chat. And right now I'm just collecting interest. So if you're interested, just email me. It's stacy@youthcodingleague.com. Again, I'll drop that in the general channel. And we'll reach out to you as we have more details when the season gets rolling in late August, early September. And hopefully we can support the Boys and Girls Club units with some local volunteers from the developer community. So I know this is being recorded, but if anyone has any questions for me too, I'm also in this Discord and I'm happy to take them now or answer them there.
Okay. Due to the audio issues, I won't even try and entertain like a Q&A thing. This is going to be awful. But as she said, in Discord, hit her up, Stacy Youth Coding League in there, and she'll drop the details in general. Please, by all means, hit her up. This is pretty cool stuff. So, Stacy, thanks a ton, and thanks for dealing with the audio stuff. By the way, it sounded perfect in here, so I know it was probably weird for you, but yeah, it was awesome. So,
yeah, I'm so glad. Thank you guys for having me. Take care.
Thanks a ton. See ya. Okay. Yeah. Oh, wait. Oh, yeah. Okay. Weird. Woo! Yep, I did. It's got the old delay. Yeah. Right. The delay is super fun. Okay, so I think Zach's going to have a lot of fun with all this stuff up here. So I'm going to turn it over and go eat some pizza. So thanks, everyone.
Is it all set up, or I mean, other than like
Yeah.
turning it on.
All right, so that's off and this is on, and you should be good to go. You probably want to turn the desktop audio back up if that's what you want to use.
Bling.
And then if you were talking about having things to pass around and show. So if you
That's gonna be at the end.
okay, so I can help with that if you need just.
Cool. All right. All right. How's that one? Oh, what? Oh, yeah, I guess there's the delay. Anyway, time travel. All right. Hello, everyone. My name is Zach Turner, and I'm here to talk to you today about NES game development, the design, the process, assembly language, the like. I'm going to assume that everyone in here works with high-level languages, C#, Ruby, Python, etc. Show of hands.
Not a machine language?
All right. So who here has actually had experience working with low-level languages? Assembly, Verilog, C, if you count it. Anyone? Okay, we got a couple people. All right. Cool, so let's start off talking about assembly. We'll just get it out of the way. Don't worry, it'll be relatively painless, and you may want a pillow for this one. Get you real comfy. All right, so assembly language, what is it? How does it work? So let's go over syntax. This is...
It's a little slow.
It is a little slow.
Slow.
Yeah. Okay, so what we have here is basically your general one-line basic instruction, or assembly, not basic. Jeez. All right. So these are going to comprise of your operand, which is the instruction itself, which is going to be shortened to 3 letters, and then you're going to have either an address or a value tied with it, because you're going to be doing something to something somewhere, or doing something with a value somewhere. Also, if anyone has any questions during any of this, just like raise your hand or something, I'll call on you. It's probably better than waiting for everything at the end, as you might forget. Anyway, so let's take a look at, so you have these instructions, but what do they affect? And what they affect is basically, these are all operating within the processor, the CPU, and to be able to use assembly, you need to know that everything is basically just registers and numbers and flags, but those are also numbers. So we're going to take a look at a statement here, which is load hex 20. Probably should have put that in here, but yeah, so anytime you see a pound sign, dollar sign together, and a value, it's going to be an immediate value. If you only see the dollar sign, that means it's memory. So in this case, LDA means load to accumulator, and the accumulator is right here. So what you're basically doing is loading, everything in here is hex. There is no decimal in here at all. So just to make that easy. So yeah, so you have the accumulator, which is effectively where all of your math happens. Everything happens through the accumulator. So when you're loading things, you're loading them into one of these registers, the accumulator, an X and a Y register. Don't worry about this right now. And basically these all hold 8 bits, so they hold a byte. So you'll load a byte in some form from memory or straight from your code. And then we have status flags, which we will get into a little later on. So let's go over an example bit of code, a small thing that I wrote up. So this would just be like a generic routine that is going to, if in your game, you are going to have probably a player object. That object is probably going to have an amount of health. So you might have a small routine to basically check whether or not they're still alive. So this would be our label. these don't really take up any space at all. They're just free. They're just for humans to understand and make this a little bit more legible. So in here, we're going to be loading a value from memory, which will be at this memory location. We're going to load that into the accumulator, and then we're going to do a compare to basically see, compares are basically subtraction, but nothing is stored anywhere. So basically we'll take the accumulator value, subtract it by this to see if they're equal, and basically, in this case, if it is greater than or equal to 0, then we're probably still alive, depending on how you're working this. So in this instance, 0 health, still basically you're alive. It's like your last hit. Because if you subtract 1 more, then you're going to underflow and go back to FF. So this is basically checking to see if we're there yet. If not, then we're going to jump between one of 2 other chunks of the code, whether or not we are dead or still alive. So because the value here is going to be greater than 0, then we're going to jump to this marker here. And yeah, so if we're still alive, we're going to still be here. But if we were 0 or below, it's going to skip this chunk or this command and execute whether or not we're our death routine. So let's get into talking about the comparisons between assembly and higher level language and what is going to make them different. So a lot of high level language is going to basically be, it's very object oriented. You're used to messing with variables and objects and the like. And this, that doesn't really mean anything. It's all user defined. There's no ints, there's no floats, there's no like strings, characters, or anything. It's all user defined. Because all you have is the CPU can view RAM and ROM being your code, and basically just bytes. It's just pulling bytes, and it's up to the programmer to define these while they're coding. So yeah, so everything happens through the accumulator and the registers like I had mentioned. So yeah, so it's just shuffling numbers, so you're gonna have non-math, which is gonna be any and all logic, and then math for calculating damage, score, lives, positioning, stuff like that. Yeah, so the interesting thing about assembly is that there's no libraries, there's no really anything. It is all you. If you want a routine like a function to basically just give you the sum of like adding 2 numbers together or something like that, you either just don't have it and it's just part of a larger part of your code, or you're going to call and jump to that function to do it for you, and it's going to return back with whatever that sum is, most likely in the accumulator. And then you just basically would call like say you want to add 2 numbers, right? So you're going to put 1 in the X, like for this example, maybe you write 1 value to the X register and 1 to the Y. And then you'll jump to your addition routine, and then when it comes back from there, say you just have your sum in the accumulator. And then now you know that that number is good, then you can continue along in your logic. At least for the purposes of this, we're all focusing on NES 6502 assembly, which is the processor. You get addition and subtraction. There is no multiplication or any division. So if you want to do said operations, you're going to have to work a little bit harder for it, unless you're working within multiplying or dividing by 2, which is where your bit shifting comes in handy. So let's take a look at that routine compared against something maybe a little more familiar. Now this is going to be about as accurate as I think it can kind of be, but it won't 100% be that accurate. We have a routine here on the left here in the assembly, and we have something in C to kind of mimic that. So in this case, we would just have like a subroutine to basically check if we're dead, and then you just have, you know, is our health less than 0, then go through and call the routine for death or not, which I included in here, but ideally, depending on how this is in your code, you may just not even need this else. It would just bounce back out of here and just continue execution. So one of the main differences in assembly compared to a higher level language is that when we're thinking about coding, typically when you're writing a script or anything, you're always assuming that it's a linear flow of how the instructions go. You're going to start at the top and it's going to work its way down, unless you have like a loop or something, and then it's going to keep going until you hit the end. That's kind of true and kind of not for assembly. It is still linear, but it likes to bounce around a lot, and it's part of the nature of how it works. So you have branches, which are statements that are basically going to be your conditionals. They are dependent on the status flags that were shown earlier that I did not discuss. And basically, the result of any math loading, comparing, is going to affect those flags. And then basically your branches are happening as a result of whether that flag is set or not. You also have jumps. So branches can jump forward, like it was shown in that example, or backwards. And it's only jumping ahead or back in code. So you could set up a loop where you need something to happen X times. So it's going to load, compare, check with a branch. And then basically, if it hasn't happened yet, this chunk down here is basically going to be your increment or whatever. If you have like your basic for loop, it's going to happen down here and send it back, check to see if it's different, and it's going to keep going. Jumps, but branches can only be, they can only jump ahead or behind 127 bytes from where they are. So you only get small movements within code. For anything larger, you would use a jump. And jumps basically can take you anywhere. They're like a branch, but they're not conditional. When something jumps and you get to a point where it jumps, it is just going to move the CPU to reading whatever is at wherever location in the ROM that you told it to. And those are typically handy for jumping to a next bit of logic, or yeah, typically jumps, you would use them more to escape a smaller routine. Where branches are typically your ifs, your else. You might use them for loops. You can use them in non-traditional ways of thinking about that, where you could have a bunch of them kind of set up in this weird way where it like jumps down here, but oh, this is met, so it's down here, and you can kind of get really clever with how many you can kind of fit in to simplify your code or use less cycles of the CPU, which is something that isn't really taken into thought in pretty much any modern programming for the most part, because computers are so fast that like if there's any real redundancies in your code, you're not really going to notice it unless whatever you're writing is incredibly demanding to begin with. You're not going to feel the bottlenecks. The other type of way that the logic flows is that we have branches and jumps, but we also have a command called jump to subroutine, which is JSR, which is basically the CPU is going to read down through your code. It's going to get to JSR and a location in the ROM, and it's going to push the current spot where it's reading onto the stack, and then do a jump to wherever you've told it to go, and which would be like a function, a subroutine, something that you're doing somewhat regularly that you just need to have in one spot. And once it's done and you get to the end, you're going to have an RTS command, which is a return from the subroutine, which will jump you back, which will pull where the pointer you've basically set on the stack. It's going to pull that off the stack and jump you back, and it'll continue execution. I probably should have shifted this in a different spot, but an example of the compare. So I was saying that compare is kind of a tricky one, but it's super interesting, and for the most part, you use it a lot, which is basically in a normal language, like say you're checking to see whether or not the difference of two values is equal to, less than, or greater than some fixed number. So instead of just taking it and you'll be like, health minus damage equals this, and is this greater than, or whatever your condition may be, to a value, you wouldn't compare that. Instead, what you would do, you wouldn't do it like that. You do a compare, which basically will do that math for you, but it doesn't actually store the result anywhere. But the status flags in the processor are affected as if it happened, and that's what you check to compare. And I didn't mention these before. There are, generally speaking, 5 that I even felt to mention here because they tend to get a little complex. And these are all just 1 bit. You have the N flag, which is negative. So if you're thinking of like a signed byte, then basically, if at any point something would have went negative or like underflowed as a result of math or compare, it's going to set this. V is an overflow. That's the opposite, where you've gone past FF. D would be decimal, if you're messing with that. Z is 0. Z is only set if literally the result in the register that you're checking is 0. It's only set then and only then. And then C is carry, which would be, say you have like a math where you're adding 2 things and you would be carrying over like an extra amount. Like, so say you're adding 2 bytes that would be greater than 256 in their 255 in their total, and they would have that remainder. That sets that, and can be handy doing some things. So in this example, we have hex 20 in the accumulator, and we're going to compare it to 10. So the way they would do it is you're going to take the 20 minus the 10, which is going to give you 10, which is only going to set. It's not going to basically set really any of this except for our carry because it's still greater than 0. And then you have the inverse here where you're going to compare to 30. So 20 minus 30 is going to be basically like negative 10. So we're going to have underflowed and went negative, and that will be set. And that's basically how you do that. All right. Let me pull this up, and I'll walk you through a small bit of code that I wrote for a game. Not that. This I may have to enhance this. How's all right.
Oh yeah, we can totally read that.
Yeah, let's just like double that.
Yeah, control scroll or something. Big one.
That help at all? Actually, how do you do this in Notepad++? I've never had to actually do it.
Do what?
Try to make the font bigger outside of just setting it in the settings.
Oh, did that not work? Does control scroll enlarge it? You hold control and scroll.
No, it's not doing anything.
How about Control Plus?
No.
Someone Google it.
Oh, yeah.
Oh yeah.
Yeah, I wasn't expecting on this projector to be such low resolution.
We'll let you know it would be worse if we were actually hooked into the VGA.
Limitations of control and scroll when it works.
Oh, how do you do this on this trackpad?
Just like 2 fingers push.
Oh.
Control and 2 fingers push.
Oh, all right, we're getting somewhere. I have to give it a second.
You might want to full screen the window too.
It's kind of there. get the Reader's Digest version of this.
You could try turning the lights off. I don't see the button. Are they motion?
Yeah, that's at least legible. Yeah. How's that? Is it better?
Helps with the assembly related names.
Yeah. We'll just skip all of that. All right, cool. So this is a script I wrote for a game on the NES for a client. I was walking through it, and we have these lovely comments, which is something you really should get in the habit of if you're going to write this, because it gets hard to parse it. Like, if you come back later, you're not going to remember how this works as easily. Like, oh, compared to what's 2 do? Or, like, why am I loading this value here? Because you're messing with, like, bit flags and abstracted kind of values that mean things, but you may forget that later. Oops. So this is a script that runs basically if you're going to use an item in the game. So we have our label here, basically checking to see whether or not the game is paused. There's just a special byte and RAM. It's doing a bit of double duty here as to whether or not the game is paused. We're basically loading that byte into the accumulator, and then we're going to compare it against 2. And the result of that is basically checking to see whether or not it is, and why wouldn't it be 1? It's a good question. I don't quite remember why, but that first bit is doing something. I don't remember what it's doing, but 2 is the bit in that byte that's basically acting as the flag to whether or not the game's actually paused. And basically, on our subtraction, like if that's not true, you can also think of a direct comparison. It's basically just, is this value equal to this fixed number? If not, then branch or do whatever. And so, like in this case, if we are paused and don't do anything, it'll just jump back, it'll RTS us back. Oh, that's right, I can just touch this thing. Man, technology's neat. So so yeah, then there's a couple things here where whether or not, like, if the game has text boxes or something, you don't want to be able to pause per se while that's going on, because you may not realize that it's paused and are waiting for it to continue, or there may not be any indicator that it is. We'll just scroll down through here, and then yeah, let's go down to, so all of these conditions are true. It's not paused, we're not in a cutscene, we're not talking to anybody, which within our logic means that we must be out in the game doing something, and we've hit the A button. So now what do? Well, we're going to load into the X register our player object's ID, or what is in that spot, and then we're going to, this is some assembly shorthand here. The get current action type is basically just going to be known as a macro, which basically is going to jump off and do a bit of code. It's basically going to be like a subroutine relative for this object that we have. So we're going to load that into the X. We're going to get the action type, which is going to fetch us back a value indicating the current state of the player. Whether we're standing still, walking, dashing, already using a weapon, etc. So we're going to compare it against 5, which in this game would be the value designated, or the ID basically, to know that if our player object state is 5, we're dashing, and we don't want to be able to use an item mid-dash. And then check to see if we are. If we are dashing, then we don't need to run any more of this, and this will jump us all the way down here and then bounce us out. If we aren't dashing, then we're going to check a few more states. And the next one is going to be to basically see whether or not, where's the, yeah, okay, yeah, there's some notes here. So then the next thing is going to be like, well, okay, so we are able to use our item. So we're in a state that we're in a state friendly to be able to use our item. So the next question is, well, do we have any like ammunition or energy or whatever it is that limits the use of this item? So then we'll check to see, we'll load another byte from the game's RAM, which in this case we have HUD slot, which is basically going to just be a set of numbers all pertaining to a different weapon, and effectively we're just going to check to see what item we have. So we're going to compare it to 3. I think this was another check for a different type of... oh, that's right, because we also need to check to see whether or not I think we have anything in hand in the first place. So then we're going to go through and basically do we're going to subtract the energy or the ammo required to use the item. I think this was testing against the... Okay, yeah, that's all commenting all of this. So that was still pertaining to movement. So now we're going to load our item's value, ID, into the X accumulator, and now we're going to do an indexed load, which is basically loading to the accumulator. If you're loading from a typical spot in memory, you're just going to load, say, like, I want to load at memory location like 20. Then you're just going to load whatever's in 20. An indexed load is basically, as you can see here, item inventory, comma X means, so let's say in this case, the item we're using is item ID 2. So we're going to load 2 into the X, and we're going to load a value into the accumulator. But so it's basically doing like an array. You're pulling a value from an array. So say you have like 8 slots because there's 8 weapons in this game. So we're just going to have that chunk in memory somewhere of all these values. So we're going to start basically from like memory 20 all the way to 28. So if you're starting at 20, and we'll assume that item inventory is memory 20, then basically it's going to be 20 comma X, and X basically being starting from here, count over X bytes and then load that, which sounds kind of clunky and weird, but it's actually incredibly handy, because otherwise you're going to, if you need to load a whole bunch of things and they're all indexed all the same way and treated like in this big chunk, a bunch of these different objects, then you can just be like, load the one offset for all of these same sized arrays, and like load this, and that. So if you need to load like an enemy and like the health for it and like all these things, well, if they're all evenly aligned and they're all here and down the line, then it's like do, and you can just populate everything in. I won't go through all of this, but I think it does give a good example of just the logic, how you have to think. Because basically all these times that you have these jumps out here, like jump done items is all the way at the bottom of this. Actually, in this case, not all of the way at the bottom. Yeah, done items is down here. Whoops. And that's just our label to call down to here, bypassing everything else. And then basically RTS is going to be our return to subroutine, because this is all treated as one big subroutine as part of the overall control scheme of what your inputs do. So every time it just goes done items, like every time it's down here, it's like, oh, well, I guess we don't need to do this. And then we just bounce and we're just going to leave. And then even within here, all these things below here, so like, even if this executes and goes all the way, we're going to hit done items, and it's going to just bounce us back. So everything below done items does get assembled and compiled into a binary, but these are basically like lookup tables, things I need to remind myself of. Like, oh, because of the way that everything's drawn into way to balance weapons, like every bit of consumption is basically based around some factor of 96 as far as how much it consumes. And then we have like ammo tables and stuff here. So like, oh, like, so every time you pick up ammo or expend it, basically that works out to like this. So like every time you use like the star weapon -1, or the 1 is subtract 2. Bombs are C. Anyone know what C in hex is? It's 12. Anyway, there's gonna be another one like that later, so you better brush on up before we get to the end of this. Dashing is 6, and all of these. It's just as a table, and that would be the thing where like this is all coded and designed so that there's 8 items. So all of your tables or anything that's going to relate to them is going to be 8 bytes long. So that way you only need to load the ID one time, load and populate everything in. This is the last part of assembly, I swear, and we're gonna get into the fun stuff. So, and then you have a couple things here like the spawning of the items in all these tables and that relate back to all of this, including changing your facing and loading in the facing and the animations and positioning of all the items. And that's just a small taste of like the steps you basically have to go through. All right, so let's pop back in. Cool. Made it to section 2. How's that feel? All right, so working with hardware. I didn't think that was going to be as appropriate when I wrote it, but holy crap. Anyway, so you write your game or your.
Do you want the lights back on, or are you gonna show stuff, or do you need the lights?
This is fine unless
Okay.
people are falling asleep or something. Anyway, so all right, I have my game. I'm going to compile it down into a binary, but where does it go? So all of the code that you write is going to be assembled or compiled down into a binary file, which is going to basically just be written to your ROM, read-only memory, because that's how all of this stuff is seen. Oh, I'm cutting off a little bit of it, but that's fine. The important part is visible. Yeah, so everything's going to be written to a ROM chip. This, if I had to guess, this board taken from an NES cart is probably Mario 1. In the early days of the NES, games were 32K. 32 kilobytes. 32,768 bytes, something like that. Anyway, so here on this graphic here on the right is basically the memory map. So when I talk about memory locations and the NES, basically everything is basically RAM or register. The address bus on the CPU. So you have a processor, and you have the ROM. And the ROM is basically just the code that is instructing the processor. So they're going to be linked, and the second that you boot the processor, it is just going to start at the first byte of the ROM and just start reading it and processing it and just going. And the bus, the address bus on the NES CPU is 16 bits, which is 2 bytes, which means that any and all memory is between hex 0, or is between register 0000 to FFFF. So any and all things, when you're loading, as far as the CPU is concerned, everything's a register. Like, you're going to read from it or write from it. So when you see things mentioned as like, as you can see here, the cart space, because when you're plugging in your game or ROM images, as you might be familiar with in the emulator scene is how they're called, is that when you're plugging that game in, you're physically like plugging the game in and completing this chunk. Oh, that's not my mouse. Right here. It's filling this spot. The rest of these things, like the top end here, above here, the interrupt, the reset, and the like, and everything below it, below 8,000, is all hardware, like the controller ports, the graphics, the audio. All of those other bits of hardware are all basically just seen as registers. So you only have between address 8000 and address FFFA for your game, or what is visible to the system as the actual program. And yeah, I would assume, and that's basically how it breaks down. You're going to have 32K for your game and 8K for your character ROM, which is basically going to be like your graphics and other assets. And I assume that this is probably Mario 1, because Mario 1 was 32K. A lot of the early games are, but most of them expanded pretty quickly after that. So you might be wondering, well, there's a lot of games that do a lot more than Mario 1. Is 32K all I get? Like, were all these games done using 32K of space? And the answer is no. When they designed the system, they left it open to expandability and designed in such a way that it could be flexible with what was using the cartridge port. So how do you get it to see more than 32K? And the answer is basically something called mappers. There would be another chip on the cart that would access some of these pins, and you would have a larger ROM, in this case like 256K. Like, now we're talking, right? So, because that's going to be 8 times as large. So the mapper basically, so if you have 256K, the mapper chip is going to be part of an interface. So when you're changing the banks or whatever the bank changing routine is, there's going to be communication between that and the chip. And basically, only a small sliver of the full 256K is ever visible to the system. So when you're doing like bank switches, like it's like, well, okay, so this whole 256K is like chopped up into a bunch of bits or a bunch of chunks. So like if you have like 8 banks, then like, well, like you're probably going to keep certain things in certain banks. So like one bank's for graphics, one bank's for sound, one bank's maybe for all of the logic. But half of that 32K is always generally visible by the system at all times. So like typically the first maybe like 8K or something is the main bank, and that's always visible no matter what, and the remaining chunk is what switches out. So any actual game logic, things that you need to call literally 100% of the time or need to be able to call 100% of the time, need to go in the main bank, and you got to try to balance and squish everything out into the residual banks. And it becomes quite a juggling act, because that means you can only cram so much code into the 8K, and then you have to try to kind of adapt it as you go. So in here, yeah, like we have 128K for the character ROMs for graphics. Extra graphics, we have extra RAM in here in addition to the RAM we already have that it would use how it's connected. Additional sound chips, the like it was hardware expandability. If you could work it in to communicate and program it right, you could basically whack it in and have it work. Action 52 is here on the side. It is not good. I don't know if anyone's familiar with it. It is noteworthy though, because Action 52 is the largest game on the system, at a whopping 2 megabytes. And if you kind of look in here, you can kind of see it where it's like we have. This is all going to be ROM. It's like ROM, and there might be like stuff down here where like maybe this is like part of the mapping and the switching to view what's available. But like the whole storage space here is the game. All right. Well, you can pile it down and you can kind of see what it is, but what does it actually look like if you're going to open it up and just view the binary? And this is a screenshot of Mario 1, a chunk of Mario, the first 220 F bytes of Mario 1 in version of HXD I have at home, which is hex editor. And effectively, I don't know if you can, kind of. So how the hex editors in that work is basically, you read it starting from the top corner, so like it's kind of just like a matrix. So like these are, so this would be 0 all the way to F. So this is byte 00, which would be the first byte. This would be your next byte, and it goes down here and then wraps around down here, and then this would be byte 10 or byte 16, and then basically it just keeps wrapping around. And effectively, when you're talking about like loading up like a thing from the ROM or something like that, you're going to be just loading like, oh hey, I need like byte like F0. Oh, and it's boom, and it's 7. We'll call back to that later. But effectively, when you pop it in, like that's just what is visible and how it's being read. So to circle back on that, there's a difference because some people talk about machine code, some people talk about assembly almost interchangeably, but there is a difference between the two. Assembly is basically the human readable, legible version of assembly, or of machine code. So if you were to compile this down, our health routine from earlier basically works out to this. So every instruction in 6502 is a byte, which means that there's potentially a max of 255 or 56 instructions that could be on the processor. As far as unique instructions, there's only 56, but we'll get back to that. So here, our load memory 200 is 80 is going to be the byte that is the load to accumulator. And then you notice that these are kind of switched around. That's only because, I don't know if anyone here is familiar with the concept of little endian formatting, as if you have more than one byte, basically everything kind of gets switched around so that it starts with the little end and kind of works its way over. So then you have your compare, seen as compare, FF would be our value. This is our branch, and I was talking about that earlier, where branches let you go forward or behind. And we'll get to that. So here's our jump. These are both the same jump, and these are the address locations within the game of where you jump to and start, you would resume execution. So our branch here, as you notice, the plus kind of skips this first jump. Now the 3 is how many bytes it is jumping ahead. If you wanted to jump behind, say like, like some, then it would be like like FC, because it's signed. So like, anyway, so yeah, so we're going to jump ahead 3 from this spot. So we're going to skip 1, 2, and 3, which means that we're going to resume execution here, which is right there. And if you view this all basically compiled down in binary, it's just going to be one massive string. And it's like, well, if you can just like write out like that, why don't people just write out like that? And there's a lot of reasons. The first thing is it'd be tedious and not impossible, but you would not want to do it. And the thing is that because we have an opcode like load or increment, it's not the same value every time. So when you do a load, it depends on the syntax of the instruction. So like, are we loading, so in case for a load an accumulator, we have immediate, and it's like, well, we're going to load a hard value. Well, then that means that the byte for that is a 9. But like, oh, if we're loading from like the first page of the memory, then it's this. If we're doing an index load, then it's this. And the length of these, even increments, if you're doing indexed X or Y, absolute or indirect, it's going to change it. And you'd have to remember all of these, and there's 56 instructions, so 56 times, you just never do it. And then also, just for something as simple as doing an increment, just upping one thing by a byte by 1. It's like, are you doing it in the first, in 0 page of memory? If you're doing it indexed in 0 page, absolute or whatever, it's going to be a different code, a different length of bytes, and a different amount of clock cycles to do so. All right, we've gotten through the hard parts. Let's get to the fun stuff. Controls, graphics, and sound. So the controller of the system, basically when you're pulling from it, you're not just reading the state. It's not going to like, give me controller state. It's not going to be like, load memory address, whatever. It's going to be, you're going to be fed the status 1 bit at a time through what's known as a shift register. And this is kind of just a good visual example of what it looks like, but effectively, you're going to have a routine set to bang out every one of these bits and then latch them, which will pop here, and then update here, and then that's basically your byte. And now once you have the byte, you can then start parsing it to figure out what buttons are held down and what ones aren't. And basically that looks like this. And these numbers here are like going to be your bits. So, bit 1, 2, 4, 8, 16, 32, etc. And then you would know, but you only know what is being held down at that moment, which you're only going to be executing a routine like this once every effectively program loop pass through the loop. All right, let's get to something more visual. All right, so what about the graphics? Oh, yeah, this is going to...
What about the graphics?
Yeah. So you get to see it a little bit here. So that the way the graphics work on this system is you effectively have 2 layers. You have a background layer, which is comprised of static tiles, and you have the sprite layer, which is generally above it, but they're 2 separate layers, and that's all you get. So when you load stuff to the background, The graphic memory here would basically be like all of your tiles. So like these would be if you have, you know, like all of these, this alphanumeric stuff up here would be like speech bubbles. If you have like a HUD, then it's going to pull stuff from here. These would be like background tiles. So if you have like, you know, like truck or forest, or like this is being used for rocks, you would be pulling these and basically taking these 8x8 chunks and moving them to 16x16 chunks and basically plotting them out within the space of a screen. You get 2 screens worth of space for this mapping. And yeah, you can kind of see the sprite work here. It's a little cut off. But yeah, so sprites can either be basically behind or in front of the background layer. And speaking of sprites, people use the sprite kind of interchangeably, because like people think of sprite when like they're talking about like playing Mario or something like that. Like people think like Mario is a sprite, and that's kind of true. But he's made up of multiple sprites because a sprite is 8x8. You get 64 total sprites to play around with, and basically all of those are going to be kind of shoved and put together and lined up to make one object if it's larger than 8x8 pixels. So you have to control and move all of these at the same time, which is why if you're playing a game that has a lot of stuff on screen and you eventually get slowed down, because a lot of processing time is being used to execute logic and move everything around, but it has to move all of these chunks around with the illusion that it's one object. You get, the NES has 8 palettes, assignable palettes, 4 for sprites, 4 for the background, 4 colors per palette, and basically that's how this would work. So these kind of show how they're assigned here a little bit. And this kind of talks about the limitation. We'll get a better example of the sprite limitation, but sprite blocks can either be 8x8, 8x16, or 16x16. You might be familiar with in some NES games, if you have too many things on the screen at one time, you might encounter what is known as sprite flicker. Sprite flicker is effectively, due to hardware limitations, you can only ever have 8 sprites on the same horizontal scan line at one time. Anything past that just does not get drawn. Games can have routines that kind of get around this, where they kind of keep track of what there is and kind of alternates what is on and what's off, but do it so fast that it isn't as noticeable. But this does a pretty good job, I think, of just kind of visualizing why that is. There's so much more to parts of this that I wanted to show in, but it is already so much. There's only like one extra thing here, which is talking about the background tile palettes. How we have some here, and basically when you're making one of these blocks, you're assigning like, oh, this pixel is using this like color of a palette, and you're assigning them all. So whenever you start to do palette changing, it's only pulling like, oh, this is color 1, and you get 4 colors. The first color is typically an transparent, so you only really kind of get 3 depending. So whenever you're switching stuff around, it's basically just you're getting a different kind of filter on it for the colors. But yeah, this is a really good example of showing just like how everything is blocked together on the background layer to basically make what you see. We'll get to audio really quick. Forgot about this. And just touch on this very briefly. And the audio of the NES is basically baked into the processor itself. Most systems around this point and later would have their own dedicated audio chip and hardware that is not dependent on the CPU as much. But with this, and to cut cost, Nintendo basically baked it in. And you basically have 5 voices. Each voice basically means you can have up to 5 different sounds playing at one time, which may sound like kind of a lot, but when you have like a song playing, but also this has to handle sound effects. So one of these channels may just be doing dedicated like sound effect duty. So now you only have basically 4, depending how you want to use it, and these are not changeable. So you only really get 2 square waves, triangle, dedicated noise, and PCM sample. The PCM sample cannot be anything else. You can't just have it do something else unless you had a sample that kind of sounded like something else and you can inject it in. I think we said this was on, right? Like the audio is good on this? Cool. And this is an oscilloscope view to basically give you a visual representation of how that works. And this is lined up the same way. You have your 2 square wave channels, you have your triangle, noise, and sample. And I try to pick something super familiar that everyone would know. This is not going to be good at all, is it? Well, I didn't think I was going to have a big delay. Oh, there we go. But yeah, you kind of see it where like you've got your melody here, this would be your bass line, here's your noise like your snare drum, and then Mario 3's main theme has like the steel drum kind of sound, and that would be dedicated here on the PCM sampling. I talked about audio expandability earlier, and the NES had it built in mind. The Japanese version of it had it in. And it actually works in North American models as well with a small mod that you can do. But there were some games that took advantage of it. None of them were released in North America, or those versions. Castlevania 3 is probably the best exception, or the best example, whereas the game we got in the US and the Japanese version had a sound expansion that provided more voices and basically just a better, richer audio experience. I was going to do a couple bits of this just to show it. This is the North American, so this has the reduced normal sound. Oh crap. Oh. Alright, anyway, the Japanese version, you should be able to tell that it sounds a little better. There's just more voices, more full. It sounds great. That's as far as the hardware goes, and this is where I was going to pass some stuff around. Yeah. I did. It's show and tell time. So we have all this stuff. We have the game. We have it on ROM and that. But like, how do we develop for it? How do we debug? How do we solve all these problems of developing software? And that's through the use of a lot of different things. So we're first going to take a look at how it was done. And as far as like early developing, it was all done with EPROMs, which, does anyone know what EPROM stands for?
You want me to pass it around, or you just want to like
Yeah, you're gonna have to come up here and just
demonstrate?
just pass it around.
Oh yeah, so you just want people to be able to look at it,
They can look at it. They can take it out and look at it too if they want.
or do we just want to like pass it around and?
So there's multiple versions of ROM. You have ROM, which is read-only memory. Then there was PROM, which is programmable read-only memory, which means you can write to it once. Once you've written to it, that's it. You just throw it away and just have to use another one. Then there was a 1E, electrically programmable read-only memory, which means that you could write to it more than once. Or that you could write to it and erase it. And then you had EEPROM, EE, which is electronically erasable programmable read-only memory, which is what's being passed around there, which are these chips that you can flash with a high voltage and basically like write to them and set all of their bytes to whatever your binary is that your compiled game. You'll notice they have a little window in the center that is a quartz glass, and effectively the thing is that you can't erase them the same way that you program them, like you would with an Arduino or something like that. Like, oh, I have a new build, and you just upload it. The way that these are erased is through ultraviolet light, high strength ultraviolet light. I like this picture here in the side because it's just someone hacking their own. It was from a Hackaday article of just, well, we have a UV LED and we're just gonna shove it right in front of the glass. Oh yeah, there's also this, which is just an EEPROM eraser. These are one of the cheaper ones, but it does the trick.
You gotta open the tray.
Oh, I should just.
So that they can see that.
Oh, yeah. So this is basically how you would manage wiping a lot of chips at one time. They make them way bigger than this, but the thing is, well, you wouldn't just a developer wouldn't just have one, because the thing is that yeah, you can erase them and rewrite them basically as many times as you want. But there's a caveat, and the caveat is this screen grab I pulled from the datasheet for one of the EEPROM chips that's being passed around, is that in order to clear all locations of the programmed contents, it is necessary to expose the chip to an ultraviolet light source. They talk about like the intensity, the dosage that you need, but you can get down here to where like the typical exposure time to erase one of these things is between 10 and like 25 minutes. So on the whole, about 15, these ones say you wipe them in 15 to 21 minutes of exposure. So you wouldn't just have one. You'd most likely have a sleeve of them or something. So it's like, oh, because if you're just like in the spot where it's like, oh, I need to make sure this one thing is like this timing's right or something, like just changes one small thing. It's like every time you want to like change and see how it works, you just got to burn it, and then, oh crap, I gotta wait 20 minutes before I can try it again. There were some workarounds for this, which we'll get to. This is an example of a development kit that was first party from Nintendo for the Super Nintendo. Just this giant box, and instead of like, you'd think of like having dev tools and boards where it's just a small module and you just kind of like connect it. Well, with this you wouldn't really be able to like do it, because like, I mean, you have a thing right here where like this thing on the front here, you can't see it too well, that's just like your socket, where this is where you'd put your EEPROM. They have a cart slot in the back. You can toggle between whether you're using like emulation or like where you're reading the data from, and it's the only way you'd be able to do it to where you would have maybe to set hardware breakpoints or any sort of debugging to have any kind of clue, like, oh, my game doesn't work, like it's working fine and it crashed. Why did it crash? I don't know. Then you just stare through your code. And with at least something like this, you would be able to probably have an idea. You'd be able to like, probably has a huge serial port on the back, or maybe even SCSI, who knows, to basically be able to like get some sort of console or feed from the system, be like, hey, this broke and this is why it happened. I thought these were really cool. These are some some old photos from when the development of the first Mario game, and basically how they were doing it, where they were having a computer map up and show like, this is how they were doing graphics. They would have like a small program to kind of handle it and everything, but like a lot of it here was just plotted on paper, because there's just a lot of math. It's like, well, we have this character with all these bytes, or all these like pixels need to like be compounded down into like a larger byte and, you know, fed to what a computer can read. This is a more zoomed out picture of that moment, where you can kind of see there's a computer here. We've got on the side here the Japanese NES, and this is the Famicom disk system. So I assume that this is how they were like quickly getting around the EEPROM issue discussed earlier, because this would take floppies. So they were probably doing a lot of some of this development. This is most likely Mario 2, like Japanese Mario 2 Lost Levels, if you're familiar with it, because this would not have existed yet. So that way it's like, oh, new build, we'll just write to a floppy and then we'll just put the floppy in, and it would be a lot quicker to do that. Here's a couple other pictures just designing things like one screen's worth of content, literally drawing it out. Like all these things here is like, oh, well, this is kind of like what we need, so this needs to look like this. Just kind of figure out like all of your tile information. Some of this was shown during the reveal or teaser for Mario Maker 2. Here is one of the stages, as far as like the entire level drawn out, so you could get a better idea of how a level flows, where things need to be, and then these would be given by the people who were designing the levels to the people programming it. And then they would basically try to punch all this in and replicate it as it was given to them. All right, well, how's it done today? There are some tools, and it does get a little bit better. So a lot of things available to you is there are emulators. Emulators are a great way to get started with that. Yeah.
Sweet, free Nintendo games. All right, you want to tell us what these are while I hand them out?
I'm getting there.
Okay.
Yep.
I'm going to get yes.
It's like, ignore the one label. That was my client who wrote that. Yeah. So
These languages in here.
yeah. So you have things like emulators. You do have some, depending on the consoles you're on. You might have your own development environment. Things like NES Maker and GB Studio are pretty great tools on the whole for single-person development for Game Boy, original Game Boy, and NES. You also have things like flashcards where, like, well, I can work on my ROM on the computer, and then once I build it all down, I can either test on an emulator, but like, okay, so it runs an emulator, but does it actually run on the actual hardware? Just as a way to confirm, and you can just put that ROM on an SD card, put it in there, boot it, plug it in, and just test it and see how it works. And maybe it's like, oh, this kind of like, maybe the emulator wasn't accurate, it actually runs a little quicker than the hardware. Maybe I can like try to cut down something, it'd be a little more efficient, get it to run faster. Flashcards and dev boards. Just a couple of the environment screen grabs. The one on the left is for the NES, where you get to see some of the graphic memory as well as some of the executed stuff. That's just a blur. All right. This is for Game Boy Studio, and it's a very similar thing where it's all nice, all in one thing. These are more recent things. For the most part, like outside of these two, I don't know of any full environments for any of this kind of stuff. You're kind of just on your own to use things like Notepad++ and an emulator that has a debugger. If it is not a Godspeed, because I don't know how else you're going to do it. I think we're...
How did they debug back in the day?
How'd they debug? It would have been if they had a kit like what was mentioned, like one of the big hardware modified system in a box. Then that would probably tell them. If they didn't, say they were maybe like a third party or something, you would have to get creative with like kind of working in like your own system. Like, oh well, I know it's like it revolves around some part in here. So like I'm gonna look at where my code is, and I'm just gonna like, before it gets to where I think it's gonna be, where it's gonna be the failure point of where it's crashing, I'll just try to like pass a value and like write it to the screen before it hits that point of a like a location in memory or something that I'm suspicious of, and then like I mean really it's like stuff like that. You've got to just kind of come up with like very clever solutions for that kind of stuff.
Here.
Pretty much. Oh, we're at the end. We are. All right. So there's one last thing I wanted to do, and that was a live hacking of Mario 1 to show you kind of, if you're interested in like old games, maybe you don't want to make your own game, but you would like to modify a pre-existing game, what the process looks like. And we're going to assume in here, we're not even going to cheat. We're not even going to try to look up online to see if, oh, hey, here's like a big chunk of it reverse engineered, or like here's a RAM map, like here's what bytes in RAM mean, and go from there. We're going to just go without it, because for some games you're just not going to have it, and for a lot of games you're not going to have it. So what we're going to do is we're going to fire up Mario 1. Show it over here. This is going to be interesting on one monitor. I'm just going to say that. So let's open. Oh yeah, this may be loud. Well, how do I turn the volume down on this thing? Is it on the top?
No, on the number row, there's a button that looks like a little speaker, speaker up, speaker down.
Oh, yeah. All right.
Yeah, Microsoft doesn't believe in hardware buttons anymore.
All right, we'll put it like 34. We'll see how it is. All right, let's just
Yeah, no audio, it's good.
Okay, cool. All right, so we have Mario 1. What do we want to do?
Flagpole skip.
So, something I was testing out a little bit earlier, to see how it's going to go. Let's say we're bad. Let's say we're bad at the game. Let's assume that. So, well, we want to make the game easier. There's a number of different ways you could probably do that if you kind of get clever about it. It's like, well, I lose lives when I die. What if that just never happened, right? Or maybe you gain lives easier, or something like that. So let's try something easy. All right. How's this on the? Cool. That's actually pretty good. So let's say we want to get more lives because we just are shedding a ton of them, dying all the time. First Goomba is kicking our butt. All right. So, well, the first thing we're going to do is we're going to start searching the memory, because if I unpause this, we're going to go into what is the hex editor, and this is going to basically, I don't know if you can see it too much. Be able to see. It's downloading. Anyway.
I can turn the lights back off if that helps.
Maybe? I don't think I can actually make this larger.
Probably
Anyway.
not. Must have good eyesight to program I can't think in this case it might be true. You can get out the Windows magnifier.
We're just going to add a window in here. Because I have to do this, because I've streamed this before, and it's quite fun, but...
Oh dear.
Alright, there we go. Yeah, give me that. Alright.
See, professional streamer.
Professional. That's,
Okay,
But we can make this larger.
okay. Got it.
Alright, let's just... we don't need to see the crown. Believe. Alright. Alright, cool. Hey, you can read it. Alright, cool. So, let's say we want to mess with coins. Because if you're going to search through memory and something, you're going to be searching, because all of the information of the game at runtime is going to be in memory. All of like things that are said or done are going to be in memory, but they're going to be numeric. So we're going to need to search the memory for a value. One's probably not a good amount to search for, because there could be a lot of different things in memory that have one that are currently 1 or 0. Let's say so, now what we're going to do is we're going to go through RAM search. We're having having an emulator with good debugging support is very handy. So this allows us, and you're not going to be able to probably see it. That's actually not too bad. So now we're going to search through memory, all of RAM, for the value 7. And this is going to be comparison, so we can look for things less than, greater than, less than or equal to, greater than or equal to, not equal to, different by, mod, whatever. So let's search through and see everything that has, oh, that's not going to turn up anything because I actually got 9. I can't even remember how many I was looking for. Anyway, boom. So now we've limited down to all of the RAM to 5 bytes that are currently 7. So now what do we do? Well, we're going to go back and pause, and we're going to keep playing the game, because this is going to update in real time. Alright, cool. We hit the block, and now we're at 10. 7EE went to 0. That's probably not anything. But these 2 bytes are now 10. So now, if we now pump in 10, we've narrowed down all of the bytes to 2. Which means that whatever byte memory that is responsible for our coin count is one of these 2 bytes. And if we keep playing, we can probably figure it out. Get out of here. They also, these 2 bytes are tied because they keep going up as I'm gaining coins. So what is most likely going on? One of these is being used for my actual coin count because you don't need to store. You only really need that 1 byte to store all of the coins you can ever have. And the other is probably being used as part of an update routine to redraw the screen, because those are not going to be connected. You're going to send that value to somewhere else, and then that value is going to be broken down for the HUD to know I need to draw all these digits. So let's try our next step here, which is, well, we know it's one of these 2, right? Well, let's just go into memory and just start writing our own stuff. Because the nice thing about FCEUX is that you can just go into memory and just start like overwriting memory at runtime and just start typing in whatever you want. So we need to hit 740. Everything I need to know. They're pretty close, which means that they're probably somewhat related. So, no. 1, 2, 3, 4, 5, 6, 7. So, let's just type in, like, 30. Oh. But, I type it in, and it just basically decrements all the way to 0. So that's probably not it. Try 75. Easy to be the count. Because this is F, this is C. We're at OC. That sounds great. Well, as I said earlier. Actually, more of a coincidence, but yes. We may have died, but our coins will carry forward. So now, is that C? So let's just, let's give ourselves a bunch of, like, let's say 1C. Now, if nothing happened, and that's probably because when you get a coin, it's going to both add to that byte, but there's that other value, but there's going to be a section of code that's going to update the HUD. So if we grab another coin, then it should update So we think that's the value, right? Coins are going to be this, are basically the amount of coins we have are stored here in memory, right? So the next thing we're going to want to do is once you have an idea of where you're wanting to look, we're going to now run a trace log, which basically is going to output in a human readable form, log every instruction that the processor runs, where it runs it, the status of the processor, the whole thing. So let's get ourselves in a position, because like these things can be huge. Like if you're even if you're running for like a half a second or so, like you could like the resulting text file could be like 100 megs if not more. So there's a coin here. So what we're gonna do is we're gonna slow down the emulation speed to just give ourselves a smaller text file. So now we're going to so now we're going to start our log. It may ask me for a file. Just slap a 2 on there. And it's going to keep recording until we tell it to stop. So now we're logging. I'm going to jump up into the... Oh, wrong. So now we're going to stop our log because in our log, we want to trigger the event that we're trying to alter because it's going to get recorded down in there somewhere. So if we have an idea of what it is, so now we have our log, right? So now we're just going to open up, backwards, log 2. Just that small amount of time, 72 megabytes. And that's why you run it at like a slow speed, so that not as much is being logged. So now we'll just open up our trace log file, and it's massive. I can actually get... So we just like look in here. That small bit was 751,866 lines of text. So now we need to find it. But that's going to be easier than you think. Spoiler. So we know, so we're just going to type in, well, we know how, because this is going to be all in assembly. It's not going to be in machine code, but they will show both. So we have an idea that address 075E is what we're looking into, right? So if we just start to search, here's our first thing. And does this look familiar? So first thing we have, increment 075E, and in here they actually tell you what it changed to, what it was, what it changed to. Increment just adding 1. When you get a coin, you get 1 coin. There's no coins in Mario that give you 5 coins or 10 coins. So increment 70, so we're increasing the value at this address. Then we're loading it, which there's your altered value here. It was 20 hex. Anybody? 32. Anyway, so we increment 30 to get 33. And then what are we doing? Well, we're doing a compare. Compare 64, which means we're comparing the amount of coins we have to the hex value 64. What's 64? If 10 is 16, then 20 is 32, 3 is 48, and 4 is 64, and 5 is 72, 6 is 96. That's the 6. 96 plus 4 is 100, which means we're checking to see if the amount of coins we have is 100. And what happens in Mario when you get 100 coins? Boom. And we basically have a branch here on the result of this condition of whether or not we have 100 coins. So it looks pretty good that what we want is right here. Well, where is it? Well, if you look right here, It is at ROM location BC0C. Where's that? Well, there's an equation you can use to kind of view it because page starts at 8,000. We're not going to go into that. Say you don't even know how to do that, right? Well, if you remember from earlier, we have our machine code right here, which is EE5E07, which is going to be increment 75E. And then you have your load AD5E07. So if we just punch this into our hex editor and just do a search for this string, because remember, everything's linear, let's do a Control F, and we'll pop this in. This is probably all the more you need. If you need more than that one line because maybe you're incrementing other things or a different thing, just start plugging in a longer string, because that's going to basically just be like, oh, it's right here. So if we search for this, boom, there it is. That is going to be... So yes, we have EE5E07, which matches the EE507. Now if we go down a line, you have the AD5E07, and if you look through here, AD5E07. So it's looking like this is it. This is where it is. And here's your byte offset 3C20. So what do we want to do? Well, the thing is that we can't just inject a whole bunch of code, because with the way that everything's a string and you have all the stuff up to this point, we only have the amount of bytes that are already there. We can't add anything, because if we add, it's going to push everything farther down. So any branches or jumps are now going to, all of your pointers are pointing that many bytes off, and your game's going to break as soon as it hits that point in the execution. So let's say, and this is why I pulled my phone out, because I don't know all of the opcodes by memory, but the internet does. So let's say, let's do it easy, all right? We have this compare at 64, right? C964. Let's say we don't get an extra life at 100 coins. How many coins should we have for an extra life? Anyone? Audience participation. 1? 5?
Yeah.
Okay. 0, 5. All right, now we're going to Control S to save. We're going to minimize this, and we're going to reload our ROM, because some emulators, depending, not all, they may be reading directly from the file, but we were able to open this, which means that it's not currently being looked at and controlled by anything else. So that means it's shoving a copy of the ROM that we're reading in memory and reading from there. So let's just reboot. And let's just take a look at our 100% official Nintendo certified copy of Mario 1. Just count along. 1, 2, 3. Well, don't worry, you can find the folder. It's right here. And if you needed any more confirmation, actually we'll get it here anyway. So, you start with 3, 4, which means we should have 9. We have more. So, well, actually, it's probably 2. It's probably 2, right? You'd have 2 because it was like the last one or something like that. 3, like, 0. Anyway. Yeah. And I mean, that's basically it. If we wanted to do something else, we could.
I think we probably want to wrap up.
Yeah, because this is basically like the tail end here. So if you want to work within this small amount of space, you could do something else like, let's see. We have 6 bytes to play with. What could you write in here? You could just skip the increment altogether. You could skip that altogether and instead load a value and write it, though that's probably not going to be as fun. You could increment twice, every coin's double. You could do something like that. Double. So let's do 20. And then we'll just copy our int twice E 507, EE 507. Reboot. Yeah, but that's basically how you do it. So if you wanted to work this into something that just alters a game like a randomizer or something, you now know the byte in ROM that you can affect, or the chunk of code, and basically have it just inject like just smaller bytes of known value to alter it and kind of do whatever you want. And but now that you know that this is like, oh, this is coins, you can kind of use that as puzzle pieces of like, well, if I can figure out like coins, lives, or something like that, you can look at the surrounding logic and try to figure out what else it's doing, start labeling it. You can eventually get your way to kind of reverse engineering the game if you wanted to do it. But I think that does it for everything I wanted to say and show off. So if there's any other questions or anything, feel free to ask.
I got a question.
Yeah.
Why would it, if you set it to increment at 5, why would it increment at 5 intervals? Or at intervals of 5? Maybe I just don't get that.
Oh, like why we're getting extra lives faster? So there's going to be like probably a bit of the logic down the way where it's like, okay, we're going to add 1. That's already a normal part of the code. Then we're going to load what we wrote because we need it in the accumulator because that increment is happening directly to memory, which means that whatever's in the accumulator could be anything. So we need to load the value that we adjusted and put that into the accumulator. Then we're comparing that against 100.
Okay.
And basically, is this 100 yet? No. Keep going. If it is, then it's gonna jump off and do the routine for basically resetting our coins to 0, getting us our extra life, playing the noise, that kind of thing.
I think I get what you mean.
Yeah. Anything else?
Is the sorry.
I may have missed it, but what tool is this?
Which one? The
Is it multiple that has like the debug option that you can do it?
oh, just the emulator?
Yeah.
That is FCEUX. It's also probably the best / most accurate NES emulator. It's great. I do any and all development on it, and if I was running any games through it, I would just use it. You can kind of see it at the top, but it's not quite there. But it is those letters: FC like Famicom, EUX. What was your question?
Is the game tick handled by that code you showed earlier, where at the end of the line you just say go back to the top?
Effectively, I didn't super touch on that, but like the way these work is that you're gonna have the CPU's reading the ROM, right? And we're just like kind of rolling through it. Well, if you've ever done any like Arduino or C kind of stuff, you're gonna have like probably like the 2 main things. We're gonna have like your void start and your like loop. Effectively, it's gonna be the same thing. You're gonna have what is gonna run like basically one time, and then it's gonna hit the program loop. And basically, it's just running a never-ending loop, and it's just like, because basically each pass through